Hello and welcome back to the Hyperthesis. We are now on the third season of our podcast. So my name is Pheely.
I'm Patrick.
And I'm Liam.
Somehow we took a little long break. I think some of us all of us have been quite busy with the beginning of new semester and things changed. I went home for a month and we did some recording there, but we've been so busy that we haven't done more since. But it's good to be back, and today we're gonna be talking about nuclear stuff. All right. Well, since we are back, are there any interesting news?
Well, I mean, there's been a lot of interesting news since we last met and recorded, but I would say one of the biggest news stories, if not the biggest news stories in science, was net positive nuclear fusion. So just last month in December, they announced from the Lawrence Livermore National Lab that they had produced more energy than was put into nuclear fusion, which is very exciting. It's honestly kind of crazy to think about because nuclear fusion has been around the corner for the past several decades. And finally, we had this net positive reaction where 192 laser beams were focused on this one, essentially little clear capsule that was filled with deuterium and tritium, isotopes of hydrogen. And by firing all of these lasers quite quickly at the same time, it compresses the gas inside to fuse, and then you can record the output of that fusion from the light and other products that are produced. And the overall return of energy was 50% higher than what was input to the system.
Well, I think now that nuclear fusion has progressed a lot. I think when I was growing up, or when we were growing up, nuclear fusion was more like a far-fetched dream. We had nuclear fission for a while, but fusion seems to be it's definitely in like the atomic bomb, but people has the idea of using it as a power source for a while, but it's just really difficult to create the condition at which the nuclear fusion can be created. And now that we have this, and I have a couple of friends working or hoping to work in the nuclear fusion industry, which are actually growing, I believe, is all these that happen. And one thing that would come out of this is it might help us in terms of the helium shortage. Because the helium is really light, so that it flies away into space. And if you working research that have to use helium, that's really expensive. Because the only place that, one of the very few places that can get it is like those air cavity underground, and they don't last forever. So those helium gas that hopefully produced from nuclear fusion, hopefully is enough for people to actually help replenish the stockpile that, or like the reservoir that's just created naturally underground.
Yeah, as someone who's probably going to end up studying ultra cold atoms for the majority of my career, the helium shortage is not a good thing because liquid helium is how you can make things really cold. And I guess I was at a party the other day talking to an experimental guy who does this kind of stuff, and he was saying that I think helium-4, there's a ton of it, but it's helium-3. So helium-4, you can get things to around like 2-ish Kelvin using it. But then helium-3, that's how you can get things to like micro Kelvin or in tandem with laser cooling. But yeah, I like that. And I think coming back to this nuclear stuff, I think there's this misconception about this net positive fusion reaction. So I had like friends approach me about it and be like, "Oh, we've figured fusion out," and I haven't looked into it, but my guess is that when they say net positive fusion reaction, it was like a very, very tiny amount of energy was created.
Yeah, I think it was on the order of maybe megajoules, but like for a very, very short amount of time, a tiny fraction of a second. So it was very small amounts of power. And so this was just an experimental test. And even though it produced 50% more energy than was input, you're running lasers to actually input it, and those lasers need cooling, and they're inefficient. They aren't perfectly 100% efficient. So ideally, you need something that produces 5 or 6 times more than the energy input to actually be effective for, say, a commercial fusion reactor.
Yeah, I feel like, at the start of everything, it's going to be kind of proof of concept. You can just do a little bit, right? And it's going to take a lot to even get it going, right? Because if you think of the atomic bomb that's have both fusion and fission, I think they create fission first, so it had enough energy for it to create fusion. And so, I mean, it's difficult to have fusion. That's why the sun is so amazing, right? It's running on fusion and creates so much energy.
Yeah, it's kind of incredible how far we've come along, though, in terms of replicating the sun. There was a really cool statistic where weight for weight, gram for gram, humans are more efficient at producing energy than the sun is. But there's just so much of the sun that these nuclear processes that happen output so much energy. But if we were to compare the power output per weight, then humans developing our ATP and then putting out power, it's so much more efficient. But that's part of the problem, is we're trying to replicate the processes in the sun, but make them more efficient so that they're actually reasonable to run on the Earth instead of relying on just this massive mass in space. Another thing I will note, what Pheely said about kind of hearing about it as we grew up. This is a very exciting result from the Lawrence Livermore National Lab, but something I remember hearing about, must have been 2 decades ago by now, was the ITER reactor and the construction of it, and it's still being constructed and put into place. So just the scale of these projects and the time that it takes to build them and construct them and do all of that is insane. And so we're seeing a lot more privatization of nuclear fusion reactors. There are many private companies now, some of which are based in Canada, actually, which are trying to figure out nuclear fusion faster than these massive research institutes. So it will be interesting to see if there's almost an arms race for nuclear fusion once we start producing positive or net positive results.
Actually, decades in terms of construction, historically, that's not much. Right? If you think of the big cathedral or in the pyramid, I'm sure it takes generations of artisans and artists to build those, even though because they don't have good technology in terms of construction. But at the time, I believe they think that these stuff they were building was as complicated as we see the new fusion reaction, like relatively, right? Like we think of the nuclear fusion reactors are like really complicated to make. It's like, well, the pyramid for them is really complicated to make, and they probably take them more than 100 years, like some cathedrals.
I did just want to share this quick fact. It took the pyramids on average 40 to 60 years to be built. They were built very quickly. But yeah, I guess we expect infrastructure projects like power generation plants to be built quite quickly. And they tend to be, but I guess they're a lot simpler in terms of mechanisms than nuclear fusion.
Nuclear power plants are just glorified steam engines, right? They can't be that hard to make. Come on.
I mean, most nuclear power plants, fission or fusion power plants, once they're constructed, will be just glorified steam.
Well, even fission, I think, right?
Well, yeah, fission is also just a steam turbine.
I'm sure you'll
at its very essence.
Yeah, I'm sure we'll talk about this soon. Anyway.
Well, the hard part is actually not creating the actual reactor. Like finding uranium is difficult, and discovering radioactivity. Even steam engine, humans we just discovered a couple, 100, 200 years ago, and we've been on Earth for like thousands of years. Like we think it's so easy, steam engine, but we haven't discovered for a long time compared to like human history. So I wouldn't say that it's as easy either.
I know. I'm just joking.
Although I have seen, I think there was a 15-year-old who built a fission reactor as a science project. So, I mean, maybe not necessarily easy, but more accessible.
So, oh, sorry. I was gonna say, how was your break, everybody? I'm just gonna quickly ask that.
Oh, my break was amazing. I went home and did some stuff, see family and friends, do some traveling with my family. Haven't done that for like ages, probably like closer to 10 years, probably 7 to 8 years. Seeing people I haven't seen for a long time, which is great. It's one strange thing I noticed is that, some of my friends I have known since like 6, 7 years old, and I know went away for a while, like 7 years. And I thought, people would change. When you meet your old friend, you're like, oh, I mean, man, they have a job now. There's some of them are married, but you kind of click back. It's like you never left. Especially I went to all boys school. They're just like, guys, just go back to like after we graduated. It's like they talk the same. They may look a little different, but I appreciate that. I hope that it continues to be like that. That people just like, I know the way they talk to other people that like they met after me or after like us, they're different. They talk different to like girlfriends or whatever. But when you go back, I'm sure it happens to you guys too. You go back to your high school buddy. It's like you never left, which is really nice.
Yeah, I didn't get up to anything wild for Christmas. I just went back home for a couple weeks, and yeah, exactly what you're saying. You go and hang out with all your old friends from high school, and you kind of like turn back into the teenage degenerate that you used to be when you're with them. Going like we walked through it was like 1 a.m. or something, and we were at my friend's house and we were all hungry and we didn't have a car, so we walked through the McDonald's drive-through like down the street because like it was open and the in-store part wasn't, so we're like, oh, all right, we're just gonna walk through. And that's like something we would have done as teenagers, but since we've come back together, we just kind of like we're acting like our old selves again. It's really funny.
Yeah, I didn't have the same experience over my break. I stayed in my new city, so it was nice because I got to spend it with some, I guess, not relatives, but in-laws, I'll call them. And then also in my break, I got to travel to Germany to work with some people at universities there for research, and got to also work at the German Space Agency, which was a childhood dream come true. That was awesome.
Very cool.
Do you speak German when you were there?
I tried my best. I was pretty successful, but when speaking these about scientific topics, I don't necessarily have the vocabulary yet.
I wonder what they think of your like Canadian accent in terms of German.
I mean, I was told it was a pretty good accent for German, so maybe I'll blend in one day.
They were just being nice.
Probably.
All right, so I think we should move on to the main topic, which, well, I don't know that much about it. I know the theory behind it a little bit, right? I think most of us know at least some kind of background of nuclear force and the nitty gritty behind nuclear physics, but a lot of them escapes me. So, anyone wanna take over the main topic, start it up? That'd be great.
Yeah. So the main topic today is about nuclear physics, and this essentially describes how atoms and their nuclei are governed, and the laws and different types of interactions that happen within them are explained. Now, nuclear physics is technically a type of particle physics, but it's so extensive that it has its own name. Like, just looking at my shelf, I have 3 different textbooks on nuclear physics alone. That's technically separate from particle physics, but it's kind of grouped under that same category. So, with the basics of nuclear physics is an atom. Now, it's a common word, you may have heard it, but might not quite understand what it is. And it's said that everything is made of atoms, or at least everything that we can see and hear and touch and feel. And while that's mostly true, it's rarely explained just exactly what an atom is and what defines an atom. So, for the most basic, I guess, definition, it's this very tiny particle that's composed of two parts, an orbiting electron and a central nucleus. So, this orbiting electron, it's not quite orbiting, but we'll just use that terminology for now. But these images of atoms orbiting this circular ball in the middle are really easy to picture, but they aren't necessarily the most true things. But they're easy to imagine.
Well, I want to add a little bit of historical perspective because atom, I think, came from the Greek. I believe that everything was made up of the smallest indivisible units, which they call atom. Like A means not. I think timos or something means divisible. So basically, it means like the smallest unit. Imagine like, well, now our current understanding of science community or scientific laws are different. We know that we can divide at what we call atoms. But back in the ancient time, they just believed that, well, maybe it's some kind of very small unit that made up everything. They just call it atom because it's not divisible into all. It cannot be broken down into smaller parts, which we know now that was not true. And we have the nuclei or nucleus and the surrounding electrons. If you are subscribed to the one electron theory,
Oh no!
you may say there's only one.
Please stop.
One electron theory regardless, atoms are composed of these nuclei and orbiting electrons. And, well, orbiting's not, I guess, the correct term for it. Realistically, the electrons actually form a kind of cloud, and it has a lot to do with quantum mechanics, and we'll definitely have to do a basics of quantum mechanics episode, just to, I guess, create a better understanding of how electrons behave. But for now, we'll just say that there's this cloud of electrons that surround an atom. And the atom, surround the nucleus, not the atom. They make up the atom. And so you have this cloud of electrons, and then you have this very dense nucleus. And that contains two different types of particles. It contains either protons or neutrons. So protons are positively charged particles that are known as hadrons. Neutrons are also hadrons. And the distinction between protons and neutrons, aside from protons being positive, neutrons being neutral, is the types and numbers of quarks that are in there. But essentially, that's the basis of an atom. It's protons, neutrons with orbiting electrons. Now, going to essentially the purest atom, we'll say, is a hydrogen ion. So in this case, it's literally just a proton. It's ionized, so there's no longer an electron orbiting it. And basic hydrogen just has one proton and no neutrons. Now, a lot can be done with this single proton, including smashing them together at very close to the speeds of light, which is done in the Large Hadron Collider. And that's how we actually get those protons, is just ionizing hydrogen atoms. Now, it is possible to also have this hydrogen atom that has a proton and a neutron. So this is known as an isotope, which essentially is a different weight because you're adding more neutrons, but the number of protons stays the same. And so with this added neutron, the weight is essentially doubled, or the mass is doubled, of the atom, or the ionized atom in this case. But you get some different properties because of this. While it doesn't add any charge, it doubles the mass, and so you get some interesting quirks from it.
Yeah, I remember learning when I first learned about like isotope, isotone, and isobar. I was like, Man, these names are ridiculous, but there are some like tricks to memorize them. But anyways, I think what's interesting is that the only thing, well, kind of the only thing that defines an element is the number of proton, right? Because helium has two, hydrogen has one, yada yada. But the number of neutrons, because they don't contain charge, you can add as many as you want. Kind of, it becomes less and less stable. So these higher, basically, you have I was thinking as like these little balls, right? The proton might be this blue ball that defines an element, and you can add this transparent neutron ball as many as you want because you can still see it as only one blue ball. But the the many transparent ball add to the weight of it and just make the atoms less stable. That's why we have this radioactivity, because those bigger nucleus would start to decay, and nuclear physics deals with nuclei or nucleus. So we talked about before that we have atoms, have electrons and stuff, but that's not part of nuclear physics. To me, the field that deal with electronic interactions are basically chemistry. It's all they deal about, right? Except for probably nuclear chemistry. But actually all chemical reactions are electronic.
Yeah, it's interesting that we define these atoms based on the number of protons, but almost all of their properties come from the behavior of the electrons. So, for example, the difference between gold and lead: gold is quite shiny, it's golden color, and lead, which is pretty kind of like a dull purplish gray. Those differences come from the nature of the electrons. So they look different to us because they have a different number of electrons, which interact differently. Whereas the protons and neutrons, they don't really contribute, I guess, physical properties that we interact with, aside from density.
Well, I would say that protons actually defines what energy levels the electrons can be. So in a way, it really influences it because it basically opens up the possibility of what it could be. It doesn't have to have all electrons in there. That's why we have all these, when you can charge or discharge an atom. But what makes the difference is that, well, you can have more energy levels, right? You can, if hydrogen only have a few because they only have one proton, we have more available energies.
Yeah, so it's the proton plays a role, but I guess not too much in the things we see because the protons attracts the electrons, which influence the behavior. But protons are very important. It's hard not to overstate that in any way because they are pivotal for defining the atom.
Yeah, when you solve the Schrodinger equation for the hydrogen atom, that's more of like a simplified view. This isn't that's not quantum field theory, but you take into account the protons via this like 1/r square potential, right? And that's what goes like. Then you solve for all the electron energy levels and stuff, and that's the protons are kind of in the simplified Schrodinger equation picture. You're not directly counting them all and stuff, but you're just saying like we have this interaction and it has a certain strength depending on your number of protons.
Yeah, to get back to nuclear a bit, the why we see fewer or less of nuclear interactions than electron interaction, because it actually has to get past that cloud per se, quote unquote, cloud of electrons to get to the nucleus. So not as many interactions. Like all chemistry reactions are electronic because it doesn't have enough energy to penetrate into the nucleus or even to interact with the nucleus, like with the nuclei. So everything is enough. There's so many variety and there's like plethora of chemical reactions that's not nuclear at all.
Yeah, and I think we'll be getting into I guess, what happens when the nuclei interact with each other just a bit later on. But before we get there, I just want to talk about how
I have a correction.
Atoms are organized.
1/r potential, not 1/r squared. Just throwing that in there.
Yeah, 1/r squared should be like force.
Yeah,
probably.
yeah, it's Coulomb potential. And then the force is r squared. Anyway.
Right. So I mean, we'll definitely delve deeper into that. But just in terms of organizing all these different atoms together, we really didn't know about atoms for quite a long time. Like we talked about before, that we've been around for thousands or hundreds of thousands of years, and we just produced a steam engine like 300 years ago. We knew about these different types of elements or atoms, again, around that same time. And as we discovered more and more, like oxygen and helium and hydrogen and all of those, we needed a system to try and classify them. Because at that point, it wasn't known that there were nuclei or how atoms were actually formed, but we just knew that there were different elements. And so it was Dmitry Mendeleev who came along and arranged these atoms based on their atomic weights, based on what he could tell. Again, around this time, it was still suggested that atoms were like billiard balls instead of this nucleus with a cloud. But Mendeleev was the first to come along and actually produce a decent system in organizing them.
Yeah, back then, this kind of physics and chemistry, they were alchemy, right? So even Isaac Newton, I think, that has the books of alchemy, and because they were the belief in chemistry was different. There wasn't any like real chemistry there because everything alchemy was trying to change one element to another. And to me, that's a lot of heuristic process or the trial and error. Right? You just try things. If it doesn't work out, you mix here and there. And it's fascinating how people actually believe that these are real, and it makes some sense because it has some experiments done on it. But when you look at it with like a modern understanding now, some are just ridiculous, like how you create gold from steel, or there's some ridiculous stuff back in the days. But we can't deny that it's a basis of what we have as chemistry and a lot of physics in today.
Yeah, it was interesting to see these great minds were convinced that alchemy was true and that you could turn lead into gold, for example. And I mean, technically, nuclear physicists or experimental nuclear physicists do alchemy, but it's a little bit different than trying to make a potion that magically turns something like lead into gold. But going back to Mendeleev, he was able to arrange the atoms within a table which depended on essentially the electron orbitals. So for different classifications of atoms, he was able to sort them into light groups, and this became known, what we see today, as the periodic table, which is something that's used worldwide. Now, there were, of course, a lot of gaps, but he was able to make suggestions for what filled those gaps and also eliminate elements that didn't fit into those gaps, which were most likely instead probably some sort of molecule or something different entirely. But after having these classified, we began to explore the properties of the nucleus more and more. And there are a couple different forces that the nucleus is subject to within an atom. And of course, the electrons too, but we'll focus less on the electrons and more so on the actual nucleus itself, since nuclear physics is concentrated on the nucleus. So there are three main forces that dictate how a nucleus behaves, and those are the electromagnetic force, the weak force, and the strong force, also known as the weak nuclear force and the strong nuclear force. Now, starting with the weak nuclear force, it's not actually weak. It's just the name for it. It's actually quite strong, but only at very small distances. And just to include that, the other of the four fundamental forces is gravity, which we just won't worry about at all right now, because that's complicated to try and coincide with quantum mechanics and still has yet to be done. So, not delving too far into the quantum mechanics of how the weak force behaves, essentially it's responsible for all of the nuclear decay that we see and all of the radioactive processes that happen within a nucleus. So there are 4 major types of decays that can happen, and they are either the emission of an alpha particle, which is just a helium atom, but without any electrons. So it's 2 protons and 2 neutrons, no electrons, and that can be emitted in these reactions. Also a gamma photon. There's also the beta particle, which is an electron or a positron, but traditionally it's just been called beta because it can be either. And then we can also get the emission of a neutron, where a neutron is actually ejected from the nucleus. Now, in terms of other processes, there are a couple that happen, mainly the electron capture process. And this is something that we were focused on in my old research for my master's. But this is where an electron, again, it's orbiting around a nucleus. It can be absorbed by the nucleus, and this resulting change causes a cascade of electrons to essentially fill the hole that the captured electron left, and it emits an X-ray. So not quite as high power as a gamma ray, but still an emission. Now, for most of these decays, aside from, I believe, the gamma emission, a new type of element is produced. And that may or may not also decay later on. And as Pheely discussed earlier, this is actually called transmutation, just like in alchemy, where you have one element changing to another. So alchemy, I guess, is happening all the time. It's within our walls, it's within us, where decays are happening and elements are being converted from one to the other. But all it is just a fundamental change in the nucleus because of some sort of radioactive decay process.
So when I think of electromagnetism, right, I think of charges, where I have I have a magnet, and I put it near another magnet, and they either if I put like a north pole to a north pole, they push each other away, or like a north pole to a south pole, they attract. Or same with electric charges, I put a plus and minus charge together, they attract. I put a plus plus charge, they repel. So in these radioactive decays, if I have some element, it's just kind of, at least from my point of view, it's just kind of sitting there doing nothing, and then after a few thousand years, it randomly spits out a neutron or something due to the strong, weak, and maybe electromagnetic forces. I don't really know. So I want to know what's going on. How are those forces causing this? Because I think of carbon dating a lot. Carbon dating is like an application of radioactive decay to date things. To look at an old historic artifact, you can carbon date it, and you can determine how old it is based on how it's decaying, how its radioactive decay is acting. But from my point of view, this old arrowhead or this old jar from this archaeological site has just been sitting there doing nothing. So what forces are going on that are causing this? I don't know.
So just in terms of radiocarbon dating, it's looking at the proportion of essentially carbon isotopes in it. Yeah, and we do have other dating processes. Like one is, for example, uranium. It's a very large atom that's quite unstable, and so it's radioactive. So if you had a chunk of uranium, chances are it's going to decay. It will take thousands of years for your chunk of uranium to turn into something else. But at the end of that decay chain is lead. And so it's an isotope of lead that's stable and doesn't decay. And so, say if we're using that dating method, we can look at the proportion of uranium to the proportion of lead and that specific isotope that's produced in it. And we can kind of tell how old something is based on how much has decayed, say within a rock or something like that. But in terms of the forces involved, I think we will have to do a particle physics episode or two to go over Feynman diagrams, because they make it really easy to visualize what's going on. Although I understand for a podcast, you can't really visualize things. But essentially, there's an interaction going on. Now, it's all completely random, but the weak force dictates this exchange of particles, essentially, where an electron might be captured. So it might just by chance happen to appear right next to a proton and whoop, be sucked into it, convert to a neutron. Because it's positive, negative, it goes to neutral and forms a neutron. So there's a lot we're still trying to understand about it, but in terms of what causes it to happen, it is the weak force, but it goes very complex into something called quantum flavor dynamics, which isn't something Guy Fieri goes into with Flavor Town, but it's quantum flavor dynamics, which relates to how these processes occur.
Yeah, it's okay. The answer is basically you just have to do QFT, and you get some probability for an atom to decay, and it's probably a small probability. So over long time periods, you eventually get kind of like a macroscopic amount of these atoms that have decayed into other atoms. And okay.
Exactly. So it's kind of like it's all statistics. So much like
Yeah.
quantum mechanics and say the position of an electron, you have to figure out where it might be, but you can never determine where exactly it will be.
Yeah, much like quantum mechanics, we don't even really understand it. So we just say, you know what, it works. Good enough.
Mm-hmm. But it's interesting because for the larger atoms that are more unstable, they are more unstable because they have more neutrons in them. So their mass is quite high, and that makes the nuclei essentially less bonded together. So, for example, if you were to try and split a helium atom, that would take a lot of energy, whereas splitting something like a uranium atom, it happens naturally. And this has a lot to do with the number of neutrons in there, because other forces like the strong force become less in the case of larger nuclei. And for something like uranium, when it splits, it can split into 2 or 3 smaller atoms, which then again might be radioactive and split again. And so this process is known as nuclear fission, where you're actually splitting an atom. So instead of just producing a single particle, such as a beta particle or an alpha particle, you're actually splitting and creating 2 new atoms. This process, known as fission, was originally discovered by Otto Hahn, Fritz Strassmann, and Lise Meitner, who did the theory behind it. So there are 2 different processes that happen in fission. Either a spontaneous decay can occur, where the atom just splits, or you can force that decay by ramming a neutron into it at really high speeds. And that's what we do with nuclear reactors. But we control the amount of neutrons that are distributed and flying throughout the uranium with control rods. However, when those control rods don't work, we get things like Chernobyl happening.
This is the same guide for the Meissner effect, the superconductor one.
Who?
Meitner, not Meissner.
Oh, not Meissner.
Yeah, different. Different person, different lady. But yeah, so this was Meitner who did all the theory behind it, and then Hahn and Strassmann were actually able to test it, which is very exciting. And then we actually started developing these nuclear reactors for testing, and it's very cool to see images of the first one because they just encased a block of uranium behind bricks. So our modern nuclear reactors have like layers and layers of concrete and lead shielding and all of that. Whereas the first test nuclear reactors, there was no fear of melting down or anything, so they just covered them in bricks, which was very fun to see. But moving away from fission reactions where the nucleus is split, there's essentially the reverse process happening where we're able to take 2 lighter atoms, and if we're able to overcome the electromagnetic force between 2 nuclei, Coulomb's force, which is what we talked about earlier, we can actually shove those 2 protons together to form a new, heavier nucleus. And so to actually do this, we need to input a lot of energy or have a lot of pressure to be able to overcome those forces. But this is what we're trying to do with nuclear fusion. So in this case, there's not really weak force or strong force taking over. It's that electromagnetic force that we have to overcome. And this can be done by having a lot of energy in the system, such as in the sun. There's a lot of pressure at a very high temperature, so the chances of two particles running into each other is quite high. Or we can try and force that to happen by, say, increasing the temperature or increasing the pressure quite a bit. And so this fusion process can happen between, well, almost any atom, but it becomes energetically favorable to do it with lighter atoms. And there's actually a really neat kind of middle point where fusion is is able to produce a net positive energy versus fission being able to produce a net positive energy, and that's with the isotope iron-56. That's kind of the most stable isotope that we know of. The chances of it decaying are essentially zero, but anything heavier than it can be fused, anything heavier than it can be fissioned, and anything lighter can be fused, and we produce a net positive amount of energy. Now, when we fuse two atoms together, like say if we had deuterium, which is a proton and a neutron, or an isotope of hydrogen, if we were to fuse deuterium with deuterium to produce a helium atom, then the mass of the helium atom is slightly less than if we were to just add the two masses together of the two deuterium atoms. And so that extra little mass that's missing is released as energy, whether as a neutron or as light. And that's how we're actually able to get energy from these reactions.
When we say the little mass that's missing, but those becomes a lot of energy, right? Because and you also have the bonding energy, and I feel like it's somehow easier to understand when we don't think about quarks, when we just think about protons and neutrons. It adds up. Oh, there's some energy that's different, but it becomes your residue energy that you get from the reaction. But when you think about quarks and even things that happen, I think this get a little more complicated.
And this fusion's also what happens in the sun, right? That's how the sun creates light and neutrinos and other things. It's the proton-proton chain, which is just fusion, but it's what you described, right? With hydrogen becoming helium and energy. So fusion is more energetic than fission, right? In theory.
Yes. In theory, if you were to fuse, say, two deuterium together, it's more energetically favorable. So I think it's something like 10 times more the energy to fuse deuterium and maybe tritium, which is one proton and two neutrons. But it's about, I think, 10 times more power is produced than if you were to split a uranium.
Yeah, so that's why people are interested in fusion reactions and fusion reactors in the futures, because we have fission reactors, nuclear power plants, but we could get a lot more energy out of fusion.
Oh, it's also cleaner, right? You don't have to deal with really unstable atoms and, what's going to happen. But if you imagine you shut the fusion down, what is going to happen with hydrogen?
Although it's very interesting because there are still issues with fusion reactors, in which some of them, like ITER or ITER, which is being constructed in France, it has, I believe it's beryllium coating along the outside for neutron capture. But because of that neutron capture that's happening to limit the amount of neutrons that are actually going outside the reactor, it's actually converting it into a radioactive material. And then, of course, there are other radioactive materials naturally occurring within beryllium that's mined. So there are issues of radioactivity also with neutron capture-based nuclear reactors. So definitely not as much as fission reactors, but still, there's a level of concern there since you're still producing somewhat radioactive elements.
Yeah, and radioactive elements in biological material tend to not get along very well, as most people are aware.
Well, the TA or teaching assistant I'm doing now, I'm doing like a fourth year laboratory, which I have to handle some radioactive material, which is pretty nice. You can have these small radiation in small pucks, but they also have like millicurie source or like usually those small pucks are microcurie. Millicurie is getting a little dangerous. I think in the basement we also have like a zero 0.1 Curie source, which is a neutron source, which is also quite finicky. So it's not supposed to be in the room for long, but it's fun to actually to not see because you can't see the radiation. You see like a ball of steel with water inside to trap the neutron. It's like, oh, you open it, there's some, a lot of radiation will come out, but just don't be there for too long. And there's a regulated amount of radiation that each person should not exceed. And actually, there is amount of radiation some people should have because I have people I know who work in a snow lab, which is in the mine underground deep without any radiation or cosmic background. And apparently, if you don't have enough radiation, like just a little bit, it's not good for your body either. So there's a healthy amount of radiation on the surface of the earth that makes human happy.
And same with radiation from the sun, right? Like if you don't get enough, what is it, vitamin D, I think, which is caused the sun hits you and your body produces it or something like that. I don't know. I'm not a UV light. Yeah, radiation, interesting topic. We should. I don't know how much we're gonna. For the sake of time, I don't know if we're gonna get into like radioactive effects on the body, but it's something to talk about one day.
Yeah, I think if we did a radioactivity episode, that'd be cool. But going back to, I guess, nuclear physics and everything involved with that, we did want to highlight nuclear fusion and fission, but there's a whole giant world of nuclear physics. One of the things I want to touch on just quickly is something known as the island of stability. So we have these very radioactive elements, and the heavier the element is, the less time it likes to hang around. So, for example, uranium has a half-life of a few thousand years, but there are some elements that are even heavier that have half-lives of microseconds or milliseconds or nanoseconds. So these are very short-lived elements that are hard to produce in a lab and even harder to try and analyze in any way. But what the island of stability suggests is that there's this, I guess, super stable region of atoms that have even more neutrons added to them, but they start to become stable. So instead of decaying in a nanosecond, it might last for a couple days or years or even decades. And so this island of stability is predicted to possibly exist for super heavy isotopes, but we're still trying to figure out where it might lie. It's a very active area of research, and there's been, I guess, better push towards it as we filled out the periodic table more and discovered more of these heavier elements, such as, I think we just completely finished the final row a couple years ago with a couple new elements. But there's a lot of research in nuclear physics to try and possibly find if this island of stability exists. But if it does, it'd be very cool, even just from like an academic standpoint, knowing that there are these super heavy elements that will last a very long time. But there are a whole bunch of other unique things that happen in nuclear physics that, if we have time, we'll maybe bring them up or mention them casually throughout upcoming podcasts. But we have things like muon atoms, or where the muon replaces the electron, and other types of nuclear fission and fusion, which are safer. And then there's also high energy experiments, which of course have my heart since I did particle physics, but so much to talk about, and I think we'll have topics for future episodes.
Yeah, we should probably talk about how nuclear reactors work. just, like how they work from like an engineering point of view opposed to kind of the theory behind the reactions. That would be fun.
Yeah, so if you are an engineer or a nuclear engineer, please get in contact with us. We would love to have you on our show as a special guest because that'd be super cool to talk about. And just if you want to contact us in any way whatsoever, you can send us an email. We're hyperthesispodcast@gmail.com. You can find us on YouTube and message us or comment on our videos. We're, again, at the Hyperthesis Podcast. You can also find us on Instagram. We're at the Hyperthesis. So you can give us a follow. You can like all our stuff. We sometimes post behind the scenes images and little fun memes. So you can get updates from us on Instagram. We are found pretty much wherever you get your podcast. So Apple Podcast, Google Podcast, Amazon Music. We're based out of Anchor.fm and are run on Spotify. But again, you can find us anywhere. So feel free to reach out to us at any time if you have questions, comments, concerns. And we're always searching for topics and guests. So if you are an expert in your field, in any region of science, we would love to have you on. And give us a follow, like, and subscribe wherever you can.
And today we got a story from Liam about the Manhattan Project. Has nothing to do with New York, but Liam, take it away.
All right. So today's story on the topic of nuclear things, it's a story about the creation of one of kind of the scariest things to ever be created by mankind, and I would argue it is the scariest thing, and that's like nuclear weapons or the nuclear bomb. So these bombs harness the power of nuclear physics, like we talked about, and I'm not going to really go into the science behind them too much, but it harnesses this power to create unmatched destructive power, the likes of which are pretty hard to comprehend or impossible to comprehend if you haven't witnessed it firsthand. They're scary to think about, so they're one of these things I try not to think about, but they're worth thinking about. So the first atomic bomb was created during this. It was the Manhattan Project had the goal of creating the world's first nuclear bomb. So it was this famous research and development undertaking which occurred during World War II to create the world's first nuclear weapons, and it was led by the United States with support from the UK and Canada. It started in 1942 and ended in 1946 after World War II was over, which was 1945. And the project was under the direction of Major General Leslie Groves of the U.S. Army Corps of Engineers, and it was led by the nuclear physicist Robert Oppenheimer, which I think we've maybe mentioned him a couple times in our podcast. I don't quite remember. But Oppenheimer was the director of the Los Alamos Laboratory, which designed the actual bombs and developed the nuclear theory behind them. So the official code name of this project was the Development of Substitute Materials Project, but eventually it was traded out with the Manhattan Project due to the location of research and development in Manhattan. And so it wasn't supposed to be called the Manhattan Project, but everyone just kind of called it that anyway, so they stuck with it. So the discovery of nuclear fission, like we talked about, it made the development of the atomic bomb a theoretical possibility, and there were rising fears among scientists and engineers that during World War II, a German atomic bomb project would be completed, and the Germans would use that to their advantage. So in August 1939, the physicists, I'm going to say this last name wrong, Leo Szilard? I'm saying it horribly wrong, I'm sure. And Eugene Wigner, so Leo and Eugene, wrote the famous Einstein letter, which warned the United States of the potential development of extremely powerful bombs of a new type. So they basically saw that Germany was going to try and develop these weapons, so they sent a letter to the president of the United States to try and take steps to acquire stockpiles of uranium ore and accelerate their own research into nuclear chain reaction so that they could actually develop their own version first. And so it was signed by Einstein and other scientists and delivered to President Roosevelt. And you know this was serious because Einstein was a pacifist and he did not believe in war at all. He was very against it, but the idea that Nazi Germany was going to create such a horrifying and destructive device first was enough for even him to recommend this kind of initiative to the US government. So that in its own right is kind of scary. The Manhattan Project, so it started out pretty small in 1939, but it grew quite large to employ more than 130,000 people and cost nearly $2 billion US dollars, which in today's market would be around 20 to 25 billion. And over 90% of the cost of this was for building factories to produce fissile material. So this is material capable of sustaining a nuclear fission reaction. And the remaining 10% was for development and production of the weapons themselves. So research and production took place at around more than 30 sites in the United States, United Kingdoms, and Canada. And their efforts initially focused on uranium-based weapons, since it was a radioactive element which could be mined directly from the Earth. And there are other reasons, I'm sure, as to why they used uranium. They started off with uranium. So when you mine uranium, the percent composition of naturally occurring uranium, it's about 99.2% what's called uranium-238. So it has 238 atomic mass units, if you know anything about chemistry. So it's an isotope, like we talked about, of uranium. So 99.2% of uranium-238, 0.72% of uranium-235, and the remainder, which is even rarer isotopes of uranium. So uranium-235 is required to create the weapons, but it's a lot rarer than the other uranium-238, since it was only 0.72% of naturally occurring uranium is this kind. So in order to overcome this obstacle, the researchers developed the process of uranium enrichment. So this allowed them to change the number of neutrons in uranium atoms and change the overall percent composition of the naturally occurring uranium which they mined. So they could use this abundance of uranium-238 and create uranium-235 out of it. So they were doing alchemy, essentially. And I'm not sure exactly how they did it, but I imagine it involves smashing neutrons around in some specific way. So scientifically accurate uranium. And so to do this, there's three different... Oh, wait, I actually do talk about the methods here. I forgot that I'd written about this. So there's three different methods. There's electromagnetic, gaseous, and thermal methods, which allow them to convert to uranium-235. So most of this work was at Oak Ridge, Tennessee, this uranium enrichment, and it actually allowed them to change the original percent composition of the mined uranium so that 85% of it became uranium-235, which is what they wanted, and it could become even higher depending on what kind of percent composition they wanted, or what kind of weapon they were working with. So for reference, reactor-grade uranium, so the uranium that gets used in fission reactors, is about 3 to 5% enriched. But for these weapons, they wanted it around 85% or higher. So in parallel with work on uranium, there was actually an effort to produce plutonium-based weapons. And plutonium was discovered at the University of California in 1940. And it turned out that plutonium was originally impractical to work with because it was actually a product of uranium irradiation. So the plutonium... Yeah, I don't quite know the details of that, but essentially the plutonium was then after it was created, chemically separated from the uranium. The Fat Man bomb, the one that was dropped on Nagasaki in Japan, was actually a plutonium-based weapon as well. So they did end up using it, but originally uranium was kind of the main element they were working with, and then they eventually discovered plutonium. And I'm not quite sure about the benefits of plutonium over uranium. Probably just a bigger explosion. Maybe it's higher yield. But the Manhattan Project also had a secondary goal, which was actually gathering intelligence on German nuclear weapon projects. So Manhattan Project personnel could serve in Europe, and sometimes behind enemy lines, where they would gather information on nuclear materials, they'd gather documents, and they were actually tasked with rounding up German scientists to come work for them. So they were trying to steal the German scientists for their own work. And many German scientists were not fond of the war effort, so they came over and helped. So despite the Manhattan Project's tight security, though, Soviet spies actually ended up penetrating the program, and then, years later, the Cold War happened. So it's this whole history behind it, which is interesting, but I'm not going to get into that too much. So in the end, we know the project succeeded its goal, which maybe isn't a good thing in the history of humans. Bombs were dropped in Japan, the first nuclear device being detonated. The first one they tested was detonated in New Mexico on July 16th, 1945. And then the Little Boy and Fat Man bombs were used a month later in the atomic bombings in Hiroshima and Nagasaki, where Manhattan Project personnel actually served as bomb assembly technicians and weapon engineers on the attack aircraft. In the immediate post-war years, the Manhattan Project conducted more weapons testing and developed new weapons, developed the network of national laboratories, and it also supported medical research into radiology. And it also laid foundations for the American nuclear navy. And they maintained control over the American atomic weapons research and production until the formation of the United States Atomic Energy Commission in 1947. So, to summarize, nuclear weapons are really scary, destructive things. There's photographs. You've seen them in movies. You've seen them in documentaries. Just how insanely, powerfully destructive they are. If an alien race existed and they saw us dropping nuclear bombs on our own planet, they would say, "What are these guys doing? Why would you ever do that? That is super dumb." And yeah, they're just a pretty. I don't like them. I think they're really bad. Although scientifically they're interesting. I always wonder if there's any other way to have dealt with World War II without them. I think that would have been the ideal scenario, but the past is the past. The best we can do now is kind of work towards never using them again. I think in a future episode we should actually talk. We have so many future episode plans we always talk about, but we should talk about the physics of nuclear detonation detection. That's a very interesting topic, actually. And what happens to nuclear waste, how they decommission nuclear bombs, and kind of the state of the world's nuclear arsenal. I think that's important stuff to talk about.
Well, I think from the tests in Los Alamos, there's radiation residue that go up into the air affects American citizens. A lot of them, actually. Is one of the largest. The clouds go everywhere, right? And on another point you had about the aliens, I'm sure the aliens have the capacity to reach us. They have probably nuclear bombed their own planet many times over.
Fair enough, but it's still like detonating nuclear device in your own planet is just, even like now that we know about it, especially because you hear about all these nuclear safety was not something people understood, and Chernobyl is a prime example of that, right? There's even like a TV show about it, which you should watch. They do a pretty good job of describing it. I've never watched it, but I've been told that.
Well, there are different doctrines of war philosophy, what to win, what is winning. I just, we can spend a whole episode talking about that, but yeah, just different viewpoint, I guess.
It's you want to win a war, you do what you do, but in the end, nuclear bombs are bad for the planet. That's not a debate. That's just a straight up fact.
All right. Thank you, Liam, for the fascinating story. We'll reconvene again next week, and hopefully we have more interesting things to say. Take care.
Bye, everyone.
See ya.